Good, we're ready to start. We are studying tests, and we saw the general concept of a test called the name and person framework, where we have a parametric model that is meant to explain the data that we see. And we want to know whether a null hypothesis that corresponds to a subset of the parameters is acceptable or not. There is a general way to formulate tests. Formulating a test means finding a rejection region that is based on likelihood ratio. This is where we completed last week, and we saw that this method consists in computing two things that correspond to estimating the model under two assumptions, under H0 or under the complement of H0, which is the same as estimating the model ignoring H0, so under the most general model. And if H0 is true, then the gain we have in likelihood should be very small. There is always a gain in likelihood because we estimate by solving an optimization problem over a larger space, but this should be very small if the true model is H0, which gives a rejection region given by a threshold posed on the gain in likelihood obtained by this method here. What we will do now is see concretely on one or two very simple examples. Then we will see what are the classical families of tests that fall into this category, which is very large. Let's come back to this model this test that we performed last week in an ad hoc fashion. We have obtained paired data, so we did an experiment with two conditions, A and B, but we had all other factors exactly being the same. So controlled experiments, probably simulations, right? And we call Xi the benefit we have of going from the first to the second factor. And we want to test whether there is really an increase, there is an improvement, which we translate in this simplistic model by assuming everything is Gaussian, and the mean of the difference is 0 under H0. There is no significant difference, so things are random, of course, but we assume that this is purely noise, the difference, versus there is a drift, there is a significant mean that is positive. This is so this is H1. So theta 0 corresponds to all values mu sigma with mu equal to 0. So let's, on this toy example, compute what is the likelihood ratio test here. It will look familiar. We have to compute the likelihood and do an optimization problem. This is exactly what we did when we studied the equivalence between least square and maximum likelihood estimation. So not surprisingly, we will find least square problem. What is the likelihood? The likelihood under the most general model is given by the PDF of a joint collection of independent random variables that are Gaussian with mean mu and variance sigma squared. So using the textbook formula, we obtain this for the log of the likelihood. Then we do two optimization problems. First, under the most global model, we solve the maximum likelihood estimation, which means we estimate mu and sigma. Sigma is a nuisance parameter, it's not really needed, but what we want is to estimate mu. This we've done already, almost. We need to maximize this, and we know that at the optimum, the value of sigma is given by this simple thing, and the optimum here is a bit different from what we saw before, because here we impose the mean mu to be non-negative. So if we look at when is that maximum? Well, the classical formula will tell us this is the sum of the mu minus the true mean square plus some quantity that is non-negative. So that is minimized when the distance from mu to the true mean, the sample mean, x bar, is minimal. Which, if the true mean is non-negative, then the answer is mu1 hat is equal to the sample mean, x bar. Otherwise, if x bar is negative, could happen, even if we are not expecting it, but it could happen because things are random. then the closest point that is non-negative is 0. So in general, we have this point here. Our estimate of mu1 under maximum likelihood and with those constraints is x bar maximum 0. And sigma 1 hat square is equal to, that is the classical formula, whenever we have an estimate of mu for a given mu, this is minimized when sigma square is exactly the mean square error, which is 1 over n, this thing here. So it's a bit different from the classical formulas we have, but it follows immediately. There's nothing very complicated. So we use those values. So we obtain a given sigma 1 hat, and we found that the log likelihood is equal to this expression, which is a constant. I mean, once I have the data, n, the number of data points is constant. It's not something I need to estimate. So it's a constant minus n log sigma 1 hat here. Right. So we see that the log likelihood, mu disappears from the log likelihood here, but it is present implicitly because to compute sigma 1 hat, we need the value of mu 1 hat here. So this is the first step we have for the likelihood under the general model. Then we re-estimate under H0. We put more constraints. We put the constraint now. We force mu to be equal to 0. So for mu, there is nothing to estimate. And then we need to find the best sigma. Then it is given by the same formula here with mu set to 0. So it is the sample mean square of the data. And the log likelihood is the same with sigma 0 instead of sigma 1. Then when we take the difference, all the constants disappear, and we find that the log likelihood is simply minus log sigma 1 hat plus n log sigma 0 hat. Right. One first thing, we will continue on the derivation, but one first thing to observe is that we see that the only thing that matters to do the test here is the variance, the estimated variance here. This is why this test here fits in the category called analysis of variance. What we do, one way to interpret what we do for such a test is to say, if H0 is true, here is the variance I will have for my data, for the errors of my data. If H0 is not true, I will have another variance, which of course will be a bit smaller. Minus log of this variance is the likelihood, so this one will be smaller. So this is interpreted classically by saying, if H0 is true, then the reduction in variance that is due to not accepting H0 by taking a more general model will be small. Right. So analyzing this reduction of variance will be the test. That's why it's called analysis of variance. But I don't like this term because analysis of variance does not allow us to really mean what this test is assuming, which is the key thing for us as users of tests. We want to know what are the assumptions. Do they make sense for us? Can we live with them? And here the assumptions are Gaussian everywhere, and with same variance, almost stochastic Gaussian. This is what is usually hidden behind the words analysis of variance. Let's continue. So the rejection region is therefore consists in saying if the difference in log likelihood is large, we reject H0, which translates to this, which is equivalent to that. So in other words, K is some arbitrary threshold that we will need to compute. So if I do this change of variable, this is equivalent to this, which is saying the variance or the standard deviation, sigma 1, the ratio of the variances should be less than something. And then if we, because the variance here has to do with the sample mean, then after some math we find that this is equivalent, if we write exactly the values that we have obtained in the previous slide for this, we will find that this is equivalent to something of this kind, where Sn is the sample mean, the sample variance computed around x bar. This is equivalent to something of that form here. Of course, here I'm not saying what is C. Oops. I'm not saying what is C. It will need to be computed. But this shows that the likelihood ratio test gives exactly a test of the kind that we had done before. Which is not surprising because, as we will see, likelihood ratio tests always find some likelihood ratio that is, at least asymptotically, when n is large, a pivot, which means the distribution will be independent of the data to a large extent, which is why we can use them, because we can compute this. Here in this case, with all the strong assumptions I've made about Gaussian and everything, I can compute what is the distribution of that under H0 to find the size of the test. To find the C, we need to say that the size of the test is, for example, 0.05. We need to compute what is the probability that x bar over Sn times square root of n, when H0 is true, is larger than C. And this can be computed. This has a student distribution under H0. So we can find this, and asymptotically it will be Gaussian when n is large. And if we take the asymptotic value, we will find this threshold here, which is the same as we had found before. So far it's not very exciting, but it is showing how this method can be instantiated. And instead of scratching your head to say, how do I design a rejection region, I have a systematic method to do it. For example, we can do it for a variant of this test where now it's the same as before, except I'm not forcing mu to be positive. I'm saying mu could be or non-negative. I test mu equals 0 versus mu anything. So more precisely here, I'm saying this is a test of whether there is a difference between the two data sets or not. Before we were saying, is there an improvement here? So we'll see whether changing H1 changes the test here. Since we have a generic method, let's do a likelihood ratio test. I skip the steps here, but we'll have also something very similar where the likelihood ratio will be this, where t is more or less the same as we had before here. And this is large when the absolute value of t is large, so the rejection region will be absolute value of t larger than some threshold here. T, like before, has a student distribution, so we can compute the threshold. For example, at a size 0.05, the threshold is 198. If we would have used the Gaussian approximation instead of student, we would have found 196. What is the p-value of this test? The correct answer is B. Let's see why. That's an example where the p-value is a bit not completely obvious. So the test statistic here is the absolute value of the sample mean rescaled by the variance. So the p-value, by the textbook definition, is the probability under H0 that this is larger than some quantity t, where t is what I have obtained, where this is the same as that, but for a hypothetical replay experiment. And we compute probabilities under H0. Right? So this is saying that's the probability that t of x has a student distribution. So it's the probability that absolute value of t is larger than t. Now we get rid of the absolute value by observing that the student is a symmetric distribution. This is hand-drawn, it's not very symmetric, but it's meant to be symmetric. So the probability that the absolute value is larger than some threshold is the sum of the probability of being larger than the threshold or smaller than minus the absolute value or minus this threshold. And those two things are equal. Therefore, the probability of exceeding here in absolute value is 2 times the probability of exceeding when we remove the absolute value. So it is 2 times 1 minus the CDF, which is here, the CDF value. Right? So 1 minus Tn minus, so T here stands for student, the CDF of the student distribution. So it's the complementary CDF. Therefore, we have a factor 2 that comes here. So if we compare the two-sided test versus the one-sided test, what are the differences? The only difference we did is in the H1. H1 was mu different than 0, whereas in the one-sided test we had a mu larger than 0. We see that the Rejection regions are different. Here we say the rejection region is the absolute value larger than 198 or 196. Here we had whenever the value is larger than some threshold, which is smaller here. Right? So the value of the threshold, the form of the acceptance region, and the value of the threshold. In practice, we're very likely to find T positive, so we might not care so much about the fact that we have absolute value, but the value of the threshold will be different. Here, it corresponds to 95%, and here, 95% of the distribution on both sides, and here on one side only. So H1 is implicitly present in the form of the rejection region, and in the associated values of the threshold, and in the p-value, consequently. So that's something to remember. Very often we tend to neglect what is H1, but we're comparing something in a given framework. If we change the framework, the results might be different. We have discussed the two-sided tests, but we could also, in this case, do something else that we know already here. Instead of testing whether mu is equal to 0, we could simply estimate mu with a confidence interval. In fact, this is what I recommend to do whenever we can have confidence intervals about a model, the parameters of a model. We have much more information, and we can reason about whether those values are large compared to what we otherwise know out of band of the system. For example, we will avoid the problem of the gray zone, whether mu is very small or very large. So if we can say something about mu, for example, here, under the assumption that everything is Gaussian, the confidence interval for mu is this thing at level 95%. Then we could say we reject mu equal to 0 when it does not belong to the confidence interval for mu here. Right? That's an alternative. That's a poor man's test, if we want. I don't know the theory of tests. This is what I would do. Well, it turns out this is exactly the same as what we did before. So that's the good news. That in this case, this is exactly the same. And this is a general result. If we have to test one specific value, so we have a parameter, that parametric model, and our hypothesis H0 is that one of the dimensions of the parameters, for example, here we had mu and sigma, now we cared only about mu, so in general I can cast that by saying I have a parametric model where the parameters has k dimensions, and the things we care about is it true that theta 1 is equal to some specific value, mu equal to 0, for example. Then a test of this is exactly the same as a confidence interval. By whatever method, you can compute a confidence interval. If you obtain a confidence interval, then you say if the true value is outside the confidence interval, then you can use it here. Right? This is exactly the same, formally equivalent. So therefore, the take-home message is, well, if we can do confidence interval, let's do it. The other take-home message is tests are in fact expanding, generalizing the idea of confidence interval for a single value by, if we're testing a number of things together, not just one value of parameter, then the test is a generalization of this here. With all the caveats we've seen about how we compute confidence intervals, we have seen there are methods that are robust, some others that are not. The same applies to tests, of course. Okay, let us see now more classically useful tests, and let's see how they are derived. One very frequently used test is called the simple goodness of fit. We'll see on the more general goodness of fit. So simple means here that we test whether a data comes from some distribution here. So I have obtained some data, x1, xn, and we are interested in knowing, is it true that it is generated IID from a certain distribution, whatever the distribution here. So not necessarily Gaussian. The goodness of fit, however, goes via some intermediate step, which consists in binning the data. So in order to be general, we look at the histogram. So essentially we say I take a histogram of the data with 10 bins, for example, like MATLAB does. I plot the histogram. I compare to the theoretical histogram I would have if F would be the true distribution. That can be computed, at least numerically, for any distribution, whether it's Gaussian or not. And then if there's a large deviation difference between the two histograms, probably it's not true. And the problem is how to quantify whether a deviation between two histograms is large. So one way to do it is to use likelihood ratio. So let's first reason about what we do once we have bins. Binning means we have sets of the values of x, of the vector x, such that we're able to compute under the assumption that f is the true distribution, we can compute qi, which is the probability that one observation falls in this set. Here. So the histogram we will have is equivalent to having the distribution, the numbers, ni. Ni is the number of samples that fall in bin I. Right? This is what MATLAB shows when we use the histogram function. Here. What is the distribution of this under H0? Right? Under H0, this is the result of an experiment where I draw something from the distribution F, and then I look in which bin it falls. So it is the same as if I know the probability is qi, drawing something that can take capital I possible values, and the value little I, the bin I, is chosen with probability qi. So it's an experiment where I have, at every individual step, I have a discrete set of choices to be made, and then we count how many times we had choice 1, how many times we had choice 2, how many times we had choice 3, etc. And the count is put in the vector n, right? And so here it's not ni, it's the vector n. That's the typo here. Then if the distribution f is truly generating the data, it must come from the distribution we obtain from doing this thing, which has a name. It's called the multinomial distribution. It's one of the combinatorial things we do in probability when we count at how many choices, which is given by this formula here. This is the combinatorial number. It's factorial n divided by factorial n1 factorial nk times the probability q1 n1, etc. Complicated, but closed form expression. Then if this is not the distribution f, then the probability of falling in bin I, the bins here are fixed, will be something, some value pi. Pi will be not exactly clear what it will be, but it will be some arbitrary p, where p must be a probability vector. So sum of the pi equal 1 and pi non-negative. So that's how we translate a hard problem in the space of distributions after binning into a more elementary probability problem. And the test now is able to test this versus that. Let's do it. Let me compute the likelihood ratio statistic. I need to compute the probability. So the probability is this. I need to estimate the model parameter under H0 and under H1. So under H0, it's easy. It's a simple test. That means the probability is given. Under H0, there is only one value, which is the thing to estimate is the vector of probability q. Under H0, it is q. We need not only to estimate, but compute the likelihood. So we need to compute what is the log of this. Well, that's very easy because this big complicated thing is in fact a constant. It's not a constant in general, but it's a constant for the optimization problem that we're doing because the data is given. So n1, n2 is my observation. And that's the empirical histogram I have. So the complexity goes away. In fact, I call this log of this a big C, and then it gives the log of this, which is sum of the ni log pi in general, or qi if we have qi here. So if I take the log of this, I will obtain this formula under H0. Under H1, we need to estimate. So I give you a histogram with pi is the proportion of objects that fall in box I. what is your best estimate of pi? So pi is the proportion, and you assume it has been generated by drawing randomly from a probability distribution. What is your estimate? Then the estimate is the naive one. Pi hat is ni divided by n, the number of items that fall in box I divided by the total number. So it is exactly the proportion, the one we would say if we would not have this theory. But the interesting thing here, it is also the maximum likelihood estimate, because the maximum likelihood translates into an optimization problem. Here it is. Maximize sum of ni log pi, that's the log of this, subject to the constraint pi larger than or equal to 0 and sum of pi equal to 1. How do you solve such a problem? Is it a hard problem? Which category of problem does it belong to? What are the hard and the non-hard optimization problems? No clue? Well, convexity is a key thing. A convex optimization problem is one for which there is a hope that there will be efficient numerical methods to find it. What is a convex problem? A convex problem is, for example, maximizing a concave function. Log is concave. Maximizing something that is concave or minimizing something that is convex, like squares, those are all convex problems. And the convex problems have the property that a local minimum for a minimization problem or a local maximum for a maximization problem is a global one, is a global one. So all we need is to go by gradient descent or other methods towards something that decreases the value if we're looking for the minimum, and that will converge to the solution. Here there's an added trick, that there is a constraint here, and one classical method to handle constraints is to use the Lagrangian. So remove the constraint by saying I will maximize this plus a Lagrange multiplier multiplied by the constraint. So sum of this plus lambda sum of pi, and then look for a solution of the non-constrained problem. Why is it easier? Because solving a non-constrained problem can be computed by setting all the partial derivatives to 0. So if we do this, we find that a closed form solution for the optimum. Therefore, after number crunching all of this, we find that the likelihood under the global problem is given by the same constant plus this. In fact, the same formula, but here we had qi, now we have pi, which is our estimate here. And the likelihood ratio, if we do the difference of the two, and we number crunch a bit, we find this is sum of the ni log ni over n over qi. So this is what the likelihood ratio statistic is. So the likelihood ratio test theory tells us that if you want to test whether a histogram truly comes from qi, the quantity of interest is this thing here. Now, how can we compute the p-value? Well, the p-value is equal to that here. Well, the p-value is equal to the probability that the hypothetical replay of the experiment would produce something larger than what we have now. Because we know a test is obtained by saying the likelihood ratio statistic is larger than something. So we know what is the generic form of a p-value for a likelihood ratio test, right? Observe here that I've twisted the problem. I'm not computing what is the value of the threshold that satisfies something. I'm transforming the problem into computing the p-value, which is in fact easier here. Well, we will see whether it's really easier. Here, how can I compute this? Well, here the assumption is that capital N, the vector of distribution into the bins, comes from the multinomial distribution with a known distribution that comes from Q, that is derived from the distribution we have. Right? It turns out that this doesn't have a closed form. We will see that when n is large, there is an approximate formula. In fact, there is an approximation formula for all likelihood ratio tests. That's why we use them. So here is an example, a historical example. This is the beginning of genetics. Mendel, as you know, he posed this theory that the reproduction of peas, in this case, is due to genes, and that every gene exists in two entities, and that when there is sexual reproduction, we randomly pick one of the two. So he did that with peas that are easier to do than with mice, at least at that time. And the peas can either be smooth or wrinkled, and they can be green or yellow. I guess the ones we usually see are the smooth green, although the yellows are considered exquisite by in some cuisines. And the question was whether the theory, the genetic theory, makes sense. And when we, according to the theory, this is the frequency we should observe of, by taking yellow male peas with wrinkled green female peas, this is the distribution of what should be seen if this genetic theory would be true. Here I'm skipping some of the biological details because I don't really know them. So the first historical example of this test was saying, well, is it true that now you do it in your garden and you find those numbers here out of a total of 500 and so peas, right? Here, the expected count is this times the total number. So how much we should find in total. So this is the NQI, right? The formulas we have here is NQI. So we can interpret that the likelihood ratio statistics is taking the log of the count divided by the expected count, right? Of course, if things are perfect, this is close to 1. Log of 1 is 0, so this will be a small number. And this is weighted by the number of things here. So I took those values. I did a Monte Carlo simulation. I simulated this random variable here. How would you do that? How would you simulate the vector n? So vector n that has this probability distribution. No clue? Well, it's very simple. N is the number I don't have zillions of things, so I don't have a scalability problem. So I can use any method that doesn't take me too much time to program, right? N1, for example, is the number of time. I have here 4 boxes. And I draw for 1p with probability 9 out of 16 whether it will fall in this box, right? So for doing the experiment for 1p is simple. We have to draw a random variable that can have 4 possible outcomes with this distribution here. We've seen that by CDF inversion. It's very simple. You draw a number between 0 and 1. If the number is less than 9 over 16, you say it is this. If it is between 9 over 16 plus 3 over 16, you say it is that, etc. That's the CDF inversion formulas that tells us we know how to generate a random variable that takes a finite set of choices. Then I do it as many times, n times, where n is the total of this, 556. I do it 556 times. And then I do the histogram. I count how many I obtain. So I have generated something that has the distribution. That is one replay experiment. Then I do it 999 times, or as many times as I need to find a good confidence interval. In fact, I didn't do it a fixed number of times, but when I do it r times, I can estimate the p-value. The p-value is this thing here, right? It is whether this quantity is larger than a fixed threshold. So if I do 1 million simulations, out of this 1 million simulations, there will be some simulations where at the end, the final output I digest from the simulation is thus this quantity. There will be some simulations that will have a quantity larger and some that will have a quantity less than or equal. Right? So I do a complete simulation, I obtain just one number, 0 or 1. Then I do it n times, and I obtain an estimation of the probability that this event is true. We have seen that it is the estimation of a failure probability, or the estimation of a success probability. So with a bit of work, we know the mathematics. I know if I've done capital R replay experiments and I've found something, I can find a confidence interval on my estimation. In fact, if it's not rare, which is the case here, I found a value around 90%. So we're not at the 99.999 something. So it's not rare, so it's fairly easy. With the central limit theorem, I will find a confidence interval. And then the trick is I did as many simulations until my confidence bound is less than 5%. Not 5% confidence. With 95% confidence, my bound is less than 5%. So the absolute accuracy of my p-value, I wanted it to be at least not more than 5%. So at least 5%, 0.05 accuracy. Sorry. With more work and more simply running my program longer, I would have obtained here a smaller confidence interval. But since the value here is very large, I don't need to refine things so much. The p-value is very large, in fact, is extraordinarily large. Therefore, we accept H0. We reject H0 when the p-value is small. So in fact, here the value is very large, so we accept the thing here. In fact, statisticians have studied this historical case. This is a historical case, so they're not numbers that are made up for this lecture. And finding such a large value is as strange as finding a very small value. Right? If you do things randomly, you could ask the question, if I do this experiment randomly, what is the probability that the p-value that I obtain is larger than 0.7, for example? And you find that this probability is very, very small. So there is some suspicion that Mendel, in fact, tweaked the numbers to have them look good, but he didn't know this p-value theory, so he just probably tweaked the numbers to make them look better than they would be in reality. Right? Okay, one small question to test things. We designed a likelihood ratio test. And the likelihood ratio test is simply saying whether a specific value of the vector of parameters θ0 is true or not. Like we had before in this Mendel P experiment. θ0 was the distribution, the vector Q, or P. P is the theta, and θ0 was Q. What is the p-value? What can we say about the p-value? Okay, well, the correct answer is A. So that's the generic thing. I have a test statistic, and the rejection region is T larger than something, so therefore I will compute what is the probability that we are larger than something, which is what we did here, right? Exactly. So that's something useful to remember. Whenever I have a method that computes a test statistic, and the test is in this form, which is the case for likelihood ratio test, then computing the p-value, at least when it is a simple test, that means whenever we're testing theta is equal to θ0 versus the opposite, then computing the p-value is simple. We don't even need to do sophisticated probabilities if we're able to do things by simulation. The problem will be when the H0 is not of this form, but H0 is truly an entire set of values, in which case the true value would be sum for theta belonging to θ0 here. That would be the p-value in the general case. And then it's more complicated because we have to solve an optimization problem, and the θ0 find so we cannot simply do it by Monte Carlo simulation. We need to do one Monte Carlo simulation for every value of theta in θ0. This would be the problem here. Okay, it's a good time to do a break. So we we break for 15 minutes, and then after the break we will see how to use simpler formulas than the one we have used so far. Each of you should have received feedback about the mini project. So the next step, as I will discuss tomorrow, is to have what is called a private defense, or an interim checkpoint. It's private because it's not public. It's just between me, one teaching assistant, and one or two people who do the test. And the idea is very early in the process that you're able to present what is your idea of the metric, of the experimental conditions, the factors, because experience shows that it takes a lot of time to develop it. I mean, do the simulations, if you do simulation, do the number crunching, if you have to do some statistical computation. So if you're not able to formulate it at the beginning of the test, you will not have enough time. So in the first week after the Easter break, we will do those presentations, where you will have to give at most 7 slides of presentation on this.